Yeah.
That makes sense. No, it is. That was. Yeah.
You did this watershed area.
No, the.
All right, so when we last met, we were talking about the fact that time dilation was not the only strange thing going on during high-speed travel, in particular, travel near the speed of light. That in fact, with the time having changed, and we're saying that our touchstone really is speed times time equals distance. If the time changes, and the speed is constant, speed of light, and nothing else go untouched, would not distance go untouched, the length. So that got us into length contraction. There was something I was just going to hint at about time dilation. There are about 3 or more different forms of time dilation. We're talking about one instance of time dilation that is spawned by Einstein's theory of special relativity. But there's also time dilation, and it's in a different form, that is due to his general law of relativity, general theory. We're not going to go over that. That's a little beyond the scope of the class. There's a third one that relates to the fact that this is something that I had hoped we would get to in this class. It would be the last chapter in this textbook, but that's not going to happen. But that would be the fact that the universe is expanding. And if you think about it, as the universe expands, light traveling at a constant speed is constantly having to pursue matter that is moving further away. And as it does that, it travels a greater and greater distance to reach us, for example. And that means that its wavelength would be shifting as the space beneath it expands. And as it turns out, time is stretched out. The time that it takes for, let's say, a 24-hour day back at the start of the universe. If we believe what the Bible says, light was created on that first day. Light is something that astronomers can see. And so if there was light created, that light would be expanding out, chasing matter across an ever-expanding universe. We're nowhere near where that light would have been created. And so what would happen to 24 hours there? That 24 hours would have been stretched according to the expansion of the universe. Turns out it would stretch probably something like 1 trillion times. So it takes that much longer to get the message from that 24-hour event that occurred. You can make an argument out of this that in fact, I do this in another class, 6 24-hour days of creation, if you were to see it now, would look like 14 billion years. That light having been stretched so far, that message coming from so far away. Kind of a fascinating thing, but it fits in with time dilation theory. So I just mentioned that as a way of saying this may have some implications well beyond what we were thinking. So we talked about the change in dimension only being in the direction of travel. So in the direction of travel, the length of the spaceship changes, but not its other dimensions. And so kind of selective in that way. Length contraction. So I wanted to spend a little more time talking about length contraction here. So here I have an example with the question is, how long is the rail car here? And so we have two observers. The woman standing on top of the rail car as it moves with a velocity v off to the right here, and an observer on the ground next to it stationary, and each one trying to measure the length of the rail car. So we need to figure out, always in these problems, you want to figure out proper time and proper length. And we have rules for doing that. So here we look at what the guy standing on the side sees. He's measuring the length of the rail car according to when the front part of it and the rear part pass this cone there. And so you can imagine he's using a timer, he's using a clock or something to measure the time when it passes that point. So because the clock is at rest in that reference frame, in his reference frame, you're at rest, and the rail car goes by at the same point with both its with both the front of the rail car and the tail end of the rail car going past the cone. So he sees proper time because he has it's at rest, and he sees the clock is at rest in that time frame. So we're going to say the length then that he sees is equal to the speed. We only have one speed, one velocity to worry about. And that's times the proper time. That would be the length of the rail car that he sees. However, the view from on top of the rail car on a different reference frame, S prime, this person believes, sees herself at rest, and she sees the cone going past. She sees the observer on the ground also moving past her with a velocity v in the opposite direction. But notice now, she says she's finding the length of the rail car by measuring the time that it takes the cone to pass her car. So a time when the cone is at, she would see it going in this direction. So this leading end would be there, and the cone going past the front and the back of the car. But when she does that, this the clock that she's using is not in the same position. It has to be in two different positions here. She does not measure proper time. However, she is free to measure the length of the rail car. She's at rest. The rail car in her mind is at rest. This is a major point that you have to sort of internalize, I suppose, that she sees the rest of the world moving past her at that velocity v. But she can measure the length of the rail car at any time, take her measuring tape, walk from one end to the other. She's not precluded from doing that. She could do it when it was still on the ground. She can do it when it's moving. And so she is measuring proper length. So she doesn't measure proper time, but she measures proper length, and that proper length, she would say, is equal to the speed of the rail car times now the time that she measures, different from the time, possibly different from the time that he measures. You're saying proper time would be different. It would be the shortest time interval that could be measured. So I have the two of them measuring these two lengths a slightly different way they're measuring it, one with speed times proper time, and the other with speed times, the time in her reference frame. And so what they have in common is the velocity. The velocity is the same in both reference frames. You could imagine if we were talking about light, this would be the speed of light having, being a constant. And so that means that those, I can ratio the lengths over the time intervals, and from that, determine a relationship between proper length and the length that he measures, that Ryan measures. So Ryan was measuring that length over here. So he measures proper time. The two events that he measures, the time interval, the front end of the back car and the back of the car, passing the cone at the same position. The cone is at rest and the clock that's measuring that ostensibly is at rest. So then we could use time dilation to figure out, so we substitute for delta t, the time dilation equation, delta t equals to delta t zero. We can make this times gamma, but I wrote it out, so divided by 1 minus v squared over c squared. And from that, we can then just use algebra to calculate that by move. I've got L here equal to my 1 minus v squared over c squared times L0, because my delta t zero is I substitute in from the time dilation equation, excuse me. So with that, we look at this factor, square root of 1 minus v squared over c squared. This is always going to be less than 1 because v is always less than c. And we can't go at the speed of light, so it never equals c, never just canceling it out. So this is a fraction times L0, meaning that that length of the car that Ryan measures, he had proper time, but she had proper length. The proper length turns out to be the greater distance, the greater length that's measured. He was measuring something shorter. So in his reference frame, that car is shorter than it was, than was measured in hers. She measures a different length. So depending on who has proper time, we're going to see them measure a different length than the other individual. So I don't know if that makes any sense to you, but I mean, it's hard to see it that way. But it's, I'll go through a couple of other things maybe that hopefully will bring this into a more understandable perspective. So we're seeing the length that each of them measures being different. What about the distance over which we could extend that and say, well, yeah, that means that the distance over which that car travels would be different for the two of them. But let's take an explicit look at that. So what happens to the distances that are traveled at these high speeds? Let's assume you're traveling to Neptune, and you have a spaceship traveling to Neptune, and then you've got the view from the Earth here. So the view from the Earth is that the spaceship is moving, flying some distance L out to the planet Neptune at a velocity v. We ignore things like turning around. We also ignore acceleration effects. Special relativity did not deal with acceleration, only with constant velocity intervals. So we would have to go to general relativity to get the expanded picture there, but that's all right. This is enough for us. we ignore the spaceship maybe turning around or slowing down to land on Neptune. So we have a constant velocity v that it travels with. So this would be the proper length. Well, why do we say that? Well, for a proper length, the observer needs to be able to measure that length at sort of any time by his standard measure of standard means of measuring that distance. We can use that at any time to measure the distance. Well, that sounds like we're measuring it in Earth's reference frame, because in Earth's reference frame, the distance between Earth and Neptune doesn't really change, not appreciably. Close to being a constant, as opposed to in the spacecraft traveling near the speed of light, its distance to Neptune is changing all the time. If he goes one day and measures the length of the trip, and another day it's going to be different. He's making time towards Neptune. Earth is not making time toward Neptune. It's not traveling toward it. So proper length, L0, would then be measured in Earth's reference frame. We've already seen that the spaceship is going to measure proper time. That was our basis in looking at time dilation originally. So the time needed for the trip from Earth's perspective is going to be some interval of time, delta t, calculated by saying it's the proper length divided by the speed of that spaceship. From the astronaut's perspective, we said the astronaut sees proper time. The clock is traveling with the astronaut. The astronaut is at rest in his reference frame. The clock is right there with him, also at rest. And another way of expressing it, I gave you a number of definitions or means to find proper time a few slides ago. And another method of looking at it is that two events, the beginning and the end of the trip, occur from the point of view of the astronaut. They occur at the same position. That is, he's at rest. He sees all of space flying past him, Neptune approaching him, and the start and end of that journey takes place with him standing right next to the clock. So these two events occur at the same position. And we recognize delta t is always greater because of that gamma factor than delta t 0. So how do we make sort of common sense out of this? So the astronauts age more slowly, they need less time. Earth would say it took them a longer time to get there than they would feel because time passed more slowly on the spaceship. So the speed is the same, but because it takes less time, they see a shorter distance. Speed times time equals distance still. And so they are measuring a shorter distance, which kind of makes sense. A shorter distance means a shorter travel time. It doesn't take as long. I should say they're traveling a shorter distance as measured by length contraction. And because of that, it takes them less time. That kind of makes sense. On Earth, they would see that it took them longer and they traveled further. But on the spaceship, they would say they traveled a shorter distance and it took them less time to do it. The length of the trip being given by the length contraction formula here, the distance traveled. So this length contraction also gives us shorter distances to travel in traveling at high speed. And notice that this factor here, 1 minus v squared over c squared, always less than 1. So the distance traveled is always less than the
than the, proper distance measured. So I realize you're probably gonna have to go through, this material several times. I've got the notes available online. This follows the textbook in most major respects. I think, some of my examples may be from other textbooks because I felt they would be a little bit, more helpful. So I would encourage you to go through the textbook. Here's an example problem. You have a cosmic ray particle. These are protons ejected by the sun and other stars. They strike Earth all the time. Here's one traveling directly over the football field from one goal line to the other, and it's traveling at half the speed of light. The length of the field between goal lines, 91.5 meters. We could do it in yards, that would be more familiar, but we're using SI units, so 91.5 meters. What length of the field is measured in the rest frame of the particle? So again, we have two reference frames to deal with, reference frame of the Earth and the reference frame of the particle, and we're looking for proper time and proper length. So we'll determine which reference frame proper length is measured in, and then we'll use the length contraction formula. So proper length is measured in that reference frame where the object being measured is at rest. The object being measured here is the football field, and that is at rest in the Earth's reference frame. If you're in the Earth's reference frame, looking at this cosmic ray particle going by, but you want to measure, you want to know the length of the field. The length stays constant in your reference frame. You're at rest, you can go out, measure the length of the field any day of the week, any time of the day, and it's going to be the same. You're measuring proper length by that definition. So L0 would be equal to the 91.5 meters. We know the speed is the same, 0.5 times the speed of light. And so we plug in the length contraction formula with L0 equal to 91.5. We put 0.5 C in for V and multiply everything out, not forgetting to take the square root. We find that in the reference frame of this cosmic ray, the field looks shorter by virtue of the cosmic ray traveling so close to the speed of light. It measures it not as 91.5 meters, but rather as 79 meters. Then we're asked, how long does it take the particle to go from one goal line to the other? What would the Earth observers see? So here we're just using speed times time equals distance. Proper time is in the reference frame of the particle. That's what we've noticed all the time. And so we're measuring the reference frame in Earth, on Earth here would be since Earth had the proper length, we have proper length divided by the velocity. We find that the time it takes would be roughly 6 times 10 to the minus 7 seconds. In the rest frame of the particle, the distance is shorter and the time is also shorter. So the time we calculate would be the shorter distance divided by that speed, and it comes out to be a shorter amount of time. The particle sees the field as being shorter, and it doesn't take it as long to cover the length of the field. It takes a shorter bit of time. This is by virtue of looking at the proper time versus time measured in Earth's reference frame. So they are kind of consistent that way. We have a shorter time being taken, but then it travels a shorter distance. We didn't have to go and create anything or manufacture anything. Any questions about the example? I think most of the time when you're doing these problems, you sort of figure out how it has to turn out, look to where the ending has to be. It's going to be shorter in one frame of reference or the other, and then You can go back and do your calculations. I think sometimes you can actually figure it that way. But always good to understand how you determine the proper length as well as the proper time. So the remainder of the chapter deals with other aspects of implications of special relativity, time dilation, etc. And mostly looking at how this gamma factor comes into play when we look at momentum, for example. In other words, we've looked at the effects of special relativity on the measurement of time and the measurement of length. We said it has no effect on width, had no effect on, depth, but on the length was affected and the time of travel was affected. Given that, it seems logical there would be impacts on other things that we looked at in classical mechanics. For example, momentum and energy. So here with momentum, there's no derivation of this. A lot of this falls out of the work that Einstein did, which involved calculations and an approach that is beyond the capabilities of our textbook and the scope of our class. So there's no derivation of this in the textbook, either this or the one for energy. So we're taking Einstein at his word here. But we're thinking that it doesn't seem illogical that the relativistic momentum would have this relativistic term in there, the Lorentz factor, this 1 over the square root of 1 minus v squared over c squared. And what it's saying from a graphical point of view, for example, is shown with the two graphs here. One is showing is plotting momentum versus time. And in that one, it's comparing the values predicted by Newtonian approaches, where Newton was not aware of any change in these factors as speed increased. So from the point of view of Newtonian mechanics, the momentum goes, right on past the speed of light without any reflection of the fact that the speed of light is the ultimate speed limit. However, with what we're dealing with, when we introduce this gamma factor, as we get closer to the speed of light, we have this 1 over a small fraction. And what that does is give us a value for the momentum that, yes, is increasing, but it never is allowed to extend beyond the value of momentum associated with the speed of light. Now, in looking at this, you might try to say, well, why didn't we, instead of looking at momentum, why didn't we just look at mass? Because from what we're saying here with the velocity constant, or I should say velocity increasing as it does here, why would the mass is not mass relativistic? And there are a lot of physicists that would accept that viewpoint. And originally that was a common view shared by most, if not all. However, the idea that this particle is increasing with its mass, becoming greater and greater. In other words, instead of plotting momentum versus time, if I was plotting mass versus time, they're saying it would look the same. You would have just a greater and greater mass, and it can't exceed the speed of light. Its mass just gets too great. But then you have to answer questions like, well, does that mean the number of molecules increased? The number of particles making up that mass increased, and it led to these arguments that said, okay, look, just to settle this, what we're going to say is that the mass does not change, but the momentum does. Momentum being something separate from the mass, so that the momentum approaches the speed of light value asymptotically and never exceeds that. The velocity itself, we look at a plot of velocity versus time, plotting the speed of light as a constant going across our graph, we would see here that the implication here is that the speed of the particle cannot exceed the speed of light. It can approach it and looks Newtonian at some of the lower values of velocity, but then departs from Newton's prediction to approach the speed of light asymptotically. That was the second of Einstein's two postulates. And so far, with, for example, the high energy particle accelerators, using more and more power to bring particles up to greater and greater speeds. These are those particle accelerators such as the Large Hadron Collider in Switzerland with a diameter of like 20 or circumference of 21 kilometers. So accelerating these particles faster and faster and faster. As much energy as they put in, all they can do is shave that distance between the particle's velocity and the speed of light ever narrower, always approaching the speed of light, but never able to exceed it. So it has been demonstrated that that's the behavior of particles as they get close to the speed of light. I think the most powerful one achieves a measure. It doesn't mean much to us now. It was called the Tevatron, and even at its most powerful, I think it was 99.9999, and then some other value. It never, at those large powers, could exceed the speed of light. So it seems like Einstein is right about the speed of light not being able to be exceeded. And if that's the case, then the momentum cannot exceed that value predicted by the speed of light either. So momentum begins to approach infinity rather than exceeding the speed of light. Now, what about some of Newton's other laws? So we talked about how Newton originally published his second law in terms of momentum, saying that the force, the net force, was equal to the time rate of change of momentum, delta P over delta T. We usually say F is equal to ma. Well, Einstein's theory of relativity is kinder to one than it is to the other here. The change in momentum, since we're calculating, we're casting momentum in this equation, which can be relativistic, that one still holds. So Newton's second law, expressed in terms of the time rate of change of momentum, would hold, but not ma, because we're not allowing the mass to be relativistic. The acceleration that this that relativity is saying is going on is getting smaller and smaller, incrementally smaller each time as the speed approaches c. And that's consistent with the high-speed particle accelerators. As they get close, they try to accelerate it to get it past the speed of light, but the increment of acceleration that you buy with each additional joule of energy is less and less. So F equals ma does not hold for relativistic speeds, but the second law, expressed in terms of the time rate of change of momentum, is still valid. I have a workout problem that's assigned. I believe you have until, well, I'm not sure. I think it's next Monday, this coming Monday, to complete the workout problems. I would encourage you to do those. I think only one person has turned one in, but they are helpful. Doing more problems can only help you in understanding these concepts. So I'll leave that one for you to work on. Relativistic energy, so energy being influenced, certainly if momentum was, then energy would also be influenced by the relativistic velocities. And what Einstein found, so again, this is distilling a lot of Einstein's work down to just a statement from which we can pick it up. Einstein found that kinetic energy wasn't just 1/2 mv squared, that it was more complex than that. So kinetic energy we're focusing on here, and he said he found that kinetic energy had to be equal to the sum of these two factors here. And the two factors, here's my mc squared, doesn't look too different from the mv squared in kinetic energy, but mv squared divided by not 2, but the square root of 1. This is our multiplied, say, by our gamma factor, or divided by the square root of 1 minus v squared over c squared. But then it has a trailer at the end of it, minus mc squared. So this is the fallout from a lot of complex work that Einstein was doing. So I can express this, turning this relativistic term back into gamma. Gamma is just 1 over the square root that's shown here. So gamma mc squared minus mc squared. I can then factor out the mc squared to give me gamma minus 1 times mc squared. And this mc squared term turns out to be what was referred to, I'm not sure that Einstein called it this, but it's referred to the rest energy. That would be the energy associated with a particle when it's at rest. Well, Newton would have said, that's her heresy right there. A particle at rest has no energy, no intrinsic energy. It only has energy when it's imbued with some velocity, and then the energy doesn't look like that. So Newton would not have agreed with this, but this is what Einstein found. And if we just rearrange this a bit, I take this equation here, I move the mc minus mc squared over to the other side where the kinetic energy is expressed here, just the term kinetic energy. I have gamma mc squared equal to what I said was rest energy plus kinetic energy. Kind of giving us to understand how Einstein viewed matter, because we had the total energy, gamma mc squared would be the total energy of the particle. We're ignoring potential energy, for example. Potential energy would just be added in as another term. There's no sense in complicating our lives with that right now. But the total energy, Einstein said, would be equal to the rest energy plus any kinetic energy that the particle has. So Newton would have said the total energy would have been equal just to the kinetic energy and not have this rest energy term here. But rest energy plus kinetic energy is what Einstein said would be the total energy. At very low speeds, not the speed of light, but something a lot lower, the total energy would have two contributions, one that Newton didn't see, one, the standard kinetic energy term that he agreed with, the combination of those two. So, and if that particle was at rest, then the kinetic energy is 0. Newton would have said the total energy would be 0, but Einstein says, no, the total energy, E, equal to mc squared. So you can see where his hallmark equation came from here. The equivalence between mass and energy, which was beyond even Newton's great understanding. So E equals mc squared falling out of the examination of kinetic energy, relativistic kinetic energy at high speeds. And in fact, it's only at high amounts of energy or high speeds that we see the energy and mass able to go back and forth. If you look at the very start of the universe, where what was available initially was all energy, and then matter precipitating out of that energy, that huge amount of energy that was available then, the matter then becoming the galaxies, stars, planets, etc., and us, as a matter of fact, precipitating in a sense out of that huge amount of energy. The on Earth here, the way in which this is demonstrated, the best way to demonstrate it perhaps, is in fission reactions. This would be in nuclear reactions such as those ongoing in nuclear power plants, such as the one out at San Onofre, no longer happening there because it's been shut down for a number of years, but in other nuclear power plants, you would find this reaction. It's also what occurs in nuclear weapons. So you have uranium-235, an isotope of uranium. You can see uranium here is the last one that has its symbol filled in here. That's the boundary line between naturally occurring elements and others that are synthetically generated, for example, in these high-speed particle accelerators, ones that typically just have extremely short lifetimes, so you don't find them naturally on the planet here. But uranium-235, the largest one, and therefore least stable, most likely to fall apart at even a hint of something else bothering it. So here we bother it with a neutron, the nucleus of the uranium being made up of 235 protons and neutrons. Now we try to add one more, and it causes the uranium to, it gets into radioactive decay. It forms a more unstable isotope of uranium, uranium-236, which immediately decays to a couple of other elements. Now, there's nothing magical about barium and chromium being the two daughter products that are shown here, because the uranium can decay and does decay into a variety of different daughter products. But what we're looking at, what we're interested in looking at here is what happens to the original masses that we had, the neutron plus the uranium-235 going to the 236. Now I add these all up here, and it looks like I ought to come out with the same number, 236 nucleons, you know, the total protons and neutrons of barium, chromium, and 3 neutrons that are given off here. But what we find if we do a mass inventory is that something has happened to some of the mass. So we have the mass of the uranium-235. This is all predicated upon being able to measure mass down to very fine increments, one of them being this atomic mass unit, which I've got on another slide here somewhere. But 235 and then some change representing the isotopes of uranium-235. I have the mass of the neutron here. I add them up. I get a certain value given in terms of the atomic mass unit U. Then I take the end products and I add them up, and going with as accurate a number as I can, and I find out that there's a difference in the mass. I'm missing some mass. I have a mass deficit. And so a mass deficit is approximately 0.186 atomic mass units And that is missing. Well, where did it go? Well, that apparently has been converted into the energy given off by this fissioning of uranium-235. So the uranium breaks down into what look like the right number of nucleons, but obliterated in there is a small amount of mass, a very tiny amount of mass converted into what is a relatively very large amount of energy by virtue of E, the energy being equal to the mass times the speed of light squared. So even though our mass deficit is very small, I have a huge number, the speed of light squared, increasing it, giving us a large amount of kinetic energy. That is one manifestation of this E equals mc squared, where mass is going to energy. There are others where energy, we have some examples of energy going to mass, but they're not as common or as easily understood as this. The rest mass is a topic we discovered a few slides ago. And so if we want to look at what is the rest mass, for example, of the proton or the electron, we could figure that out. So we basically assume that we can still measure the work done in the proton moving through a 1 volt potential difference. So I have the work done equal to Q times the voltage difference. There's nothing controversial there, introduced by relativity. This would be equal to the single charge represented as the E times 1 volt. This gives us a new unit to use when discussing energy. It would be 1 electron volt would be the amount of work done in moving a single charge through a voltage difference of just 1. If we look at the mass of the proton, we take that 1.67 times 10 to the minus 27. We would say that's equal to mass. So that gives us a total rest energy of mc squared. So the mass of the proton times c squared, but then expressing it in terms of these electron volts, we would find that that gives us a number 938 million electron volts, where my electron volt is just E times 1 volt. So we can write the mass of the proton. You can write the mass of the proton as just E over c squared, or the number of any MeVs, 938 MeVs divided by c squared. It's the million electron volts. The electron volt is basically the term of preference that's used in physics in talking about the physics of some of these small particles. And so you may find, I think in your homework, I've given you a couple assignments using this. So you need to be familiar with that way of looking at energy. I think that's all the time we have today. And I'll ask Dr. Cummings to pick up from here, but we're very close to the end of the chapter. After this, we're going to go on to chapter 27. So the next one in the next one. That will be the last one we're able to cover this term. If you have any questions, you can see me during hours or send me an email, etc. All the usual methods.